Okay, so we're going to look at a really interesting way of factorising polynomials using matrices. So for example, this polynomial, x squared plus y squared, you can actually show that it's not possible to factorise this in the conventional sense using real numbers. It is possible to factorise this using complex numbers, but our approach is actually going to just use real numbers, and we're also going to involve matrices. So this isn't going to look like a conventional factorisation into two terms in brackets. What this is actually going to look like is a factorisation into a product of two matrices. And here there's a conceptual leap we need to take, which is to reimagine our x squared plus y squared. Instead of being x squared plus y squared, you can perhaps imagine this in brackets being multiplied by an invisible 1. We're going to imagine this being multiplied by an invisible identity matrix. So the idea here is then, instead of working with x squared plus y squared, we'll actually work with x squared plus y squared times an identity matrix. And we want to factorise this into the product of two matrices A and B like this. So if we start looking for a solution, let's just say in the 2 by 2 case, to keep things simple, what we're really looking for is x squared plus y squared, 0, 0, x squared plus y squared for our x squared plus y squared times the identity matrix, and we want this to be somehow equal to the product of two matrices A and B. Now if you're familiar with finding the inverse matrix for a 2 by 2 matrix, you may recognise this structure as, let's imagine we've got a 2 by 2 matrix A, B, C, D, and we start inverting this, so we swap our A and D, we take the negative of our B and C, then to find the inverse, we would just take all of these and divide by the determinant AD minus BC of the original matrix. But if we don't divide by the determinants, then the matrix that we would get will be of the form AD minus BC, 0, 0, and AD minus BC. So it's AD minus BC times the 2 by 2 identity matrix. So this structure is actually quite useful now, because you can see that this matches up with what we're trying to achieve. We want x squared plus y squared times the identity matrix, and using this insight from knowing how to invert a 2 by 2 matrix, we can get something of this form, AD minus BC times the identity matrix. So it makes sense now. We can say, let's say our AD is x squared, so we could take A is equal to x, D is equal to x, we could say negative B is equal to y, and let's make c equal to positive y. Then we know, just using this nice insight from the inverse of a 2 by 2 matrix, that if we take our A as x, our B is going to be negative y, our C is positive y, and D is x. So we take this as our ABCD matrix and multiply this now by our D, negative B, C, A matrix. We multiply this by x, y, negative y, x, just using our values for A, B, C and D that we've identified there. You know that we're going to get x squared plus y squared times the identity matrix. So x squared plus y squared with the two zeros, and an x squared plus y squared down there. So you can show then that x squared plus y squared can indeed be factorised in the sense of turning it into the product of two matrices, so long as we're willing to accept our x squared plus y squared multiplied by an identity matrix there. And we can actually apply the same procedure to factorise more complicated looking polynomials like this one, so long as we've just got the sum of two different terms. So we can use this exact same structure of setting this equal to AD minus BC, and here you can see there's actually some choice over what we choose to be our A and our D. So for example, we could have A equals x, and we could have D equals y to the 5, or we could also have chosen A was xy and D was y to the 4, and there's other possibilities there as well, depending on how we want our factorisation to look. Then for our BC, let's take negative b equal to 3z squared, for example, or we could take c equal to z squared, so that AD minus BC matches up with our original expression. So then if we use this fact about the 2 by 2 matrices, we get that the matrix with x, then b is negative 3z squared, our c is z squared, and d is y to the power of 5. If we multiply this now by the d, negative b, negative c, a matrix, so we've got y to the 5, positive 3z squared, negative z squared, and x. When we multiply these two matrices together, we'll get back to our original expression, x y to the 5 plus 3 z to the 4. In the first entry we get a 0, and another copy of x y to the 5 plus 3z to the 4. So we get that this is indeed the product of our original expression and the 2 by 2 identity matrix. But if we want to factorise a polynomial that has 3 or more terms in it, so for example x squared plus y squared plus z squared, then our previous approach isn't quite going to work. We can still factorise the x squared plus y squared part using 2 by 2 matrices, and we could even do the same for the z squared part on its own. So we could treat z squared as AD minus BC, where, for example, we could say A and D are both equal to z, so we get a z squared. We could say that B and C are both equal to 0, so that we just get z squared minus 0. So in this sense, we can write z squared multiplied by the 2 by 2 identity matrix as z0, 0, z, where we've got A and D are both equal to z, and our B and C are both equal to 0. So we get a factorisation for z squared as well. And what's interesting about having the factorisations for the separate pieces we want to add together is we could try adding these matrices together now. So when we add together both matrices, we get x squared plus y squared plus z squared multiplied by the 2 by 2 identity matrix is now going to be the product of these two matrices plus the product of these two matrices. So if we call these two A and B, and we'll call these two C and D, we can see that our x squared plus y squared plus z squared times the 2 by 2 identity matrix is equal to AB plus CD. So this still isn't very helpful because this doesn't count as a factorisation. It's not the product of two matrices, but it's a step in the right direction. And actually, if we consider higher dimensional matrices, if we go all the way up to a 4 by 4 matrix, let's have a look at x squared plus y squared plus z squared multiplied by the 4 by 4 identity matrix. So here we're going to have x squared plus y squared plus z squared on each of these leading diagonal terms and zeros elsewhere. So now when we're working with quite large matrices, it can help us to use block matrices where we split our matrix up into smaller submatrices just to make it more manageable to work with. So here, this 4 by 4 identity multiplied by x squared plus y squared plus z squared, I'm going to split up actually into 4 copies of 2 by 2 matrices. So here we'll have x squared plus y squared plus z squared on the leading diagonal terms. You'll just have zeros for each of these blocks. But then for our x squared plus y squared plus z squared on each of these leading diagonal terms here, we've actually just got 2 copies of x squared plus y squared plus z squared multiplied by the 2 by 2 identity matrix. So we have 2 copies of exactly this expression up here, and we've got one down here in our 4 by 4 matrix. So the key insight then is that this is equal to AB plus CD, so we can write AB plus CD in these entries here to represent exactly what's going on with our 2 by 2 submatrix here and our 2 by 2 matrix down here. We've just got copies of this AB plus CD structure, where we're now representing this as block matrices. So this is a 2 by 2 matrix, this is just 0, 0, 0, 0, a 2 by 2 0 matrix, and so is this. And here again we've got the 2 by 2 matrix formed by adding AB plus CD. Then you'll see that this actually starts to resemble our AD minus BC structure like before, and we'll build on this by making sure that our block matrix satisfies certain properties so that we can get it to behave like this factorisation we had earlier, only now our A, B, C and D are actually 2 by 2 matrices, whereas here they were just real numbers. Now before we proceed with our block matrices, I think it's worth just spending a little bit of time exploring exactly how multiplication works with block matrices. So we'll just work through a quick example where you've got 2 4 by 4 matrices multiplied together, and they're both split up into 4 2 by 2 matrices, like so. So if we want to carry out the multiplication here, we would just start by multiplying everything in this first row by everything in this first column, and that would give us our top left entry in the new matrix evaluated from the product. So you would have A11 E11 plus A12 E21 plus B11 G11 plus B12 G21. And at this point you might actually notice some of the structure. A11 times E11 plus A12 times E21. This is exactly the same as what you would get if we were just multiplying the A matrix by the E matrix. So A11 and A12 get multiplied by E11 and E21 here. We add them together. So this piece here is actually the same as if we had A times E and we just took the top left entry of this. And similarly for our B and G, this is actually just the same as if we took the top left entry of B times G. But then we're still adding all of this together. So actually if we were to take the AE matrix, add this top left entry to the top left entry of our BG matrix, then you'll see that this is actually the same as having, if we were to just do AE plus B times G and take the top left entry. And we could do a similar process for example, for the next row, and we could multiply all of these terms by the first column. And if you have an experiment with this, you can convince yourself that block matrix multiplication really works just like regular multiplication. So the upshot here is that I want to be able to say that when we multiply all of these blocks, you'll just get AE plus BG as our top left block. So the multiplication is really just like with a regular matrix, and in the bottom left we'll have CE plus DG, and similarly for the top right AF plus BH, and finally in the bottom left we're going to have CF plus DH. So because we have this structure of when we multiply each of the individual pieces and add them together, we have the exact same thing as if we did A times E and B times G and added them together. For each of these entries in the top left, we'll get AE plus BG for our top left block of the matrix, and similarly for each of the other blocks of the matrix. So then we'll be able to use this now to find a nice way of factorising our x squared plus y squared plus z squared using block matrices. So if you remember, we had this expression where we had x squared plus y squared plus z squared times the 4x4 identity matrix, expressed as a block matrix like this, where we have the zeros and we have this repeating AB plus CD structure there. And now we want to see if we can somehow factorise this block matrix using what we now know about how block matrix multiplication takes place. You can see it's very similar to how regular multiplication takes place. So we could try and go for, we want our AB plus CD down here with the capital letters to match up with our lowercase ad minus bc. So we could try A lowercase is equal to capital A. We could try D is equal to lowercase b, just abusing the notation somewhat here. We could have negative lowercase b, we replace that by c, capital C, and finally our capital D would correspond to the lowercase c. So lowercase c, capital D. So then if we substitute this into our ABCD matrix like this, we'd have A for lowercase a, our B would be negative C, lowercase c would be capital D, and lowercase d becomes B. Then we'll multiply this by B, C, negative D, and A. So then when we expand this and we carry out the multiplication, we get in the top left AB plus CD, which is exactly what we're looking for here. So we're hoping to get AB plus CD, 0, 0, AB plus CD. Let me just draw the lines in as well, just to make it really clear that these are block matrices. So now we've got our AB plus CD. Then if we go to the top right entry, we want this to be 0. We get A times C minus C times A. And now when we're working with real numbers, A times C minus CA would just be equivalent to 0. But here, because we're working with matrices, AC isn't necessarily the same as C times A, because matrix multiplication isn't always commutative. So here, this isn't necessarily going to be equal to 0, so we might need to choose our A and C very carefully so that this still works. And similarly for the bottom left, we get DB minus B times D. So again, we would actually need DB to be equal to BD, so we need to choose these matrices carefully so that this works. And even for our bottom right entry, we get DC plus BA. So if we want this DC plus BA to be equal to AB plus CD, we need quite a lot of constraints. So we actually want, first of all, we want AB to be equal to BA, so that our BA term down here matches up with our AB term that we want. We also need DC to be equal to CD, so that this DC term matches up with our CD term down there. And finally, we also need, for the top right and bottom left entries to both be equal to 0, we also need AC equals CA, and we need DB equals BD. So we want all of this so that our matrix then is equal to AB plus CD. Then we do have the zeros if this is all true, and we would have AB plus CD in the bottom right as well. So that then we could factorise our intended matrix here as A negative C DB, B C negative DA, like so. So now we need to deal with choosing our A, B, C and D so that we can guarantee that all of these properties here are satisfied. And we're quite fortunate in this regard because our choice of matrices C and D are actually just scalar multiples of the identity matrix. So there's a property that if you have a scalar multiple of the identity matrix, and this will commute with any square matrix of the same size. So what we're saying in general is then, if you have lambda as a scalar multiple of an identity matrix I, we multiply this by another square matrix of the same size M, this is always going to be equivalent to M times lambda times I. So we'll have this commutativity property. So this actually gives us three of our equations are satisfied by default. So we'll have AC is equal to CA, we also have DC equals CD, and we get DB equals BD, just because C and D are both multiples of the identity matrix. So now all we need to do is check that our AB is indeed equal to our BA, and then we'll be able to factorise our matrix. So you could check this by hand for this example, just by multiplying B times A, you can verify that this is the same thing as having A times B. The only issue now is we could actually do this in even more generality, because we followed a structure here of having a matrix A, B, C, D, and multiplying this by almost the inverse, where you've got D, negative B, negative C, A, and we get AD minus BC, 0, 0, AD minus BC. But then we can verify if we multiply these the other way round, we do our second matrix multiplied by our third, you can verify actually that D minus B minus CA multiplied by AB CD is also equal to AD minus BC 0, 0, AD minus BC, this multiple of the identity matrix. So we can actually say more generally then, AB is always going to be equal to BA, and you can see now that this method is looking like it will work more generally as long as we follow this structure of using the ABCD rule here, D minus B minus CA. As long as we're following that structure to get our first matrix for our first few terms, then we throw in another term for our z squared using multiples of the identity matrix, it looks like we're always going to get this commutativity property so that we can then factorise our 4x4 matrix. Now let's see what the factorisation for x squared plus y squared plus z squared times the 4x4 identity actually looks like now that we've verified that this is indeed going to work. So we're going to have A minus C DB as our first matrix, where each of these are our block entries. So our A matrix in the top left, we have x, negative y, y, x. Then our D in the bottom left, we have z, 0, 0, z. Then we move over to the top right, we have negative the C matrix, so negative z, 0, 0, negative z. And finally we've got our B matrix in the bottom right, so x, y, negative y, x. So this is our first 4x4 matrix in this factorisation. Then we're going to have BC negative DA for our second matrix in this factorisation. So we have B is xy negative yx in the top left. In the top right we've now got positive C, so z, 0, 0, z. In our bottom left we have negative z, 0, 0, negative z. And finally in the bottom right we've got our A matrix, x, negative y, y, x, like this. And you can verify if you like, if you were to multiply out both of these matrices, you would indeed get x squared plus y squared plus z squared times the 4x4 identity matrix. And perhaps now you can see how we might be able to generalise this method for any polynomial made up of 3 terms. So if we return to x times y to the 5 plus 3z to the 4, which you've already factorised as a 2-term polynomial, but we're also going to add 2xz to this and see if we can factorise this using 4x4 matrices. So if we want to factorise this, we can first of all factorise our 2xz, just as, for example, 2x and z separately, each multiplied by the identity matrix. And then we've got something in this form with a, b, c and d. We've got multiples of the identity matrix so that cd is going to be equal to dc and so on. And then we can just factorise this exactly like before, so that then x y to the 5 plus 3z to the 4 plus 2xz, all multiplied by the 4x4 identity matrix. This is now going to be equal to, using our block matrices, we'll have a in the top left corner, so our x negative 3z squared, z squared, y to the 5. Then we've got our negative c in the top right, so negative 2x, 0, 0, negative 2x. In the bottom left we've got our d matrix, z, 0, 0, z, and we've got b in the very bottom right, so y to the 5, and we've got positive 3z squared, we've got negative z squared, and finally x. So this is our first 4x4 matrix in the factorisation of this. Then we multiply this now by the bc negative dA matrix. So just to fill this in, we have our b matrix, y to the 5, 3z squared, negative z squared, x. For our positive c, we have 2x, 0, 0, 2x. Then in the bottom left, we've got negative d, so negative z, 0, 0, negative z. And in the bottom right, we've got our a matrix, so x, negative 3z squared, positive z squared, and y to the power of 5. So you can check, if you like, if we multiply both of these matrices together in this order, then we'll get xy to the 5 plus 3z to the 4 plus 2xz times the 4x4 identity matrix. And now we'll just finish by looking at how we could generalise this to include a 4th term in our polynomial, and you'll see how the method could be extended to include 5, 6, 7, even more terms in our polynomial. So let's imagine we've got a polynomial made up of 4 different pieces, and we've already done the work for p plus q plus r. So we've got p plus q plus r times the 4x4 identity matrix working just like before. We get this factorisation to the product of 2 matrices, we'll call them k and l, which are made up of block matrices just like this, with our a, b, c and d having the nice commutativity properties. So we've got our c and d will be a product of just a scalar with the identity matrix, and our a and b will commute so that ab is equal to ba. And finally, we'll say that our new term that we're adding in, s, if you multiply this by the 4x4 identity matrix, we can just split up any of the terms in s into 2 different products with the identity matrix. So here we'll call this m and n, where both m and n are just scalar multiples of the 4x4 identity matrix. So now we can add together this s times the identity plus p plus q plus r times the identity. And just like before, we'll get p plus q plus r plus s times the 4x4 identity matrix is now going to be kl plus mn. And again, we can go up a dimension or two here. So we can go up to p plus q plus r plus s. And if we actually multiply this by the 8x8 identity matrix, then the idea behind doing this is we then get a block matrix, which is kl plus mn in the top left, 0 in the top right, 0 in the bottom left, and in the bottom right we get kl plus mn. So then we've got the 8x8 identity matrix multiplied by p plus q plus r plus s is something that is in this right sort of form that we could attempt to factorise now using block matrices. So just like before, we'll actually be able to factorise this into the product of 2 block matrices. So we'll have k here, we'll have l here, we'll have negative m here, we'll have positive n here, where this is all a block matrix. And if we multiply this by l, positive m, negative n, and k in the bottom right here, this block matrix, you can check that we'll get our kl plus mn. And again, in the bottom right, you'll get k times m minus m times k, for the top right. Then for the bottom right, we'll get nm plus lk. But fortunately, it turns out that these commutativity properties are still shared by these k, l, m, and n as a result of the work we've done earlier in choosing our a, b, c, and d. So for example, m and n, we already know are going to commute with any matrix of the same size because they're scalar multiples of the identity. So we haven't gone into too much detail here, but hopefully you can see how this procedure could then be extended to adding in another term, and we'd go up to a 16 by 16 identity matrix. So you can see here this perhaps isn't the most efficient way to factorise things using matrices, but I think it's really interesting how essentially just using this insight from inverting 2 by 2 matrices and a little bit of knowledge of how block matrices multiply, we can genuinely factorise any polynomial using matrices.